Write C++, and the compiler translates it directly into machine code, instructions meant exclusively for the physical hardware on your desk. Java takes a different route. The famous promise of write once, run anywhere is only possible because Java doesn't compile directly to native hardware. It targets a highly controlled intermediary layer. To actually master Java, you have to look past the syntax on your screen and understand the software architecture running underneath it. You are writing logic for a mechanical system managed entirely by a virtual machine. The system's outermost boundary is the JDK, containing the compiler and build tools. Nested inside is the JRE, providing class libraries to run code. At the center sits the Java virtual machine. The JVM translates platform-independent bytecode into specific machine code for any hardware. To prevent this translation process from slowing down execution, the JVM relies on a just-in-time or JIT compiler. The JIT identifies frequently used bytecode and compiles it into native machine code on the fly, drastically accelerating performance. But abstracting the hardware away comes with a cost. To keep this simulated environment from crashing, the JVM imposes strict rules around memory management and data typing. When you write Java, you aren't talking to your computer's physical processor. You are feeding logic into this strictly controlled, simulated execution pipeline. When the JDK compiles your source code, it doesn't output an executable program. It generates a .class file, an intermediate format that looks like gibberish to a human reader. This image shows what the JVM is actually reading, dense arrays of hexadecimal opcodes. Translating these raw hex values reveals mechanical instructions like aload_0. Notice the A prefix, telling the JVM it is manipulating an object reference, whereas an I indicates an integer. The JVM enforces strict data typing here. Back on the developer side, we feed data into the system by declaring variables, named memory locations that the JVM will populate during execution. The simplest way to assign a value is by using a literal. This is a constant value hard-coded directly into the source code. Literals follow strict formatting rules. You might use binary formats or even hexadecimal formats. These hard-coded literals are distinct from user-generated input variables, which the JVM must allocate and populate dynamically at runtime. Regardless of how elegantly you structure your variables or format your literals, the compiler aggressively strips that abstraction away. It reduces every declaration down to those strictly typed hexadecimal instructions. This chart outlines how the JVM organizes variables into distinct memory paradigms. On the left is the primitive branch, including foundational data types like Boolean, char, and int, which store simple, raw values. Primitive values are stored directly in stack memory. The stack is highly ordered, rapidly accessible, and strictly limited in scope. The non-primitive branch handles complex data like user-defined objects. Requiring too much space for the rigid stack, they are stored in the heap, a dynamic pool of unstructured memory. The JVM places a pointer in the stack linking to that object's address. Whenever a method is called, the JVM creates a new, isolated stack frame. Java uses a strict pass-by-value rule, always copying the exact value into the new frame, rather than relocating the original data. This leads to a pervasive misconception. Developers assume Java uses pass-by-reference for objects, but Java is strictly pass-by-value. It copies the reference address, resulting in two identical stack pointers aiming at the exact same heap object. Because both pointers target the same heap location, mutating the object's properties inside the new method will successfully alter the shared data. But because the method only holds a copy of the pointer, it cannot reassign where the original variable points. The original reference remains untouched. This strict pass-by-value architecture ensures that a method can never accidentally reassign a variable in the caller's scope. It creates a firewall around local state, maintaining predictable data boundaries even as information is shared across complex applications. This rigid division between stack and heap creates a mechanical conflict. Advanced data structures, like generics, demand heap objects. They structurally reject stack-based primitive data. The architectural solution is the wrapper class, object shells designed to encapsulate primitive values. Through a process called autoboxing, a primitive integer is wrapped inside a shell, migrating its storage into the heap for compatibility. Data must also move between different primitive types. This explicit translation process is known as typecasting. The JVM safely handles widening conversions, moving small data into larger memory spaces. However, narrowing conversions require explicit developer approval, because squeezing large data into a small memory slot risks permanent data truncation. Once your variables are successfully cast and stored, the JVM uses strict rules to evaluate complex nested expressions. Rule 1 is operator precedence. Just like in algebra, certain operators structurally override others. The JVM will prioritize multiplication over addition, completely bypassing a simple left-to-right reading. Rule 2 is associativity. Equal precedence uses a left-to-right tiebreaker. Rule 3 is operand evaluation. Operands are evaluated strictly left to right in memory. Here, A executes before B, and D and E before C, regardless of structural precedence. Expression resolution in Java is entirely deterministic, stripping away any ambiguity regarding exactly how state changes will execute in memory. Pulling back from all of these micromechanics reveals exactly how these individual rules form a single interlocking system. It begins in the input phase, utilizing the tools of the JDK to declare literals and construct complex expressions. Then comes translation. The compiler enforces typecasting and autoboxing, ultimately compressing your logic into dense hex bytecode. During execution, the JVM engine takes over, mechanically sorting that data between the rigid stack and the dynamic heap. And governing all of this is the absolute pass-by-value rule, securely isolating data transfers between every method frame. Memorizing superficial code syntax is a fragile approach to engineering. Understanding system architecture builds robust, adaptable intuition. Ultimately, mastery of the language is found in visualizing the virtual machine, moving far beyond the high-level syntax to see the deterministic engine that executes every line of your code.